I wanted to continue our discussion of derivative formulas by introducing probably the most powerful of all the differential rules that we'll have. It's called the chain rule, and it is super important. So let's just go to it. I will say that this rule tells us how to deal with derivatives of composite functions, and it actually ends up expanding the usefulness of some of the previous rules that we've already learned. This is a big one. I know this looks a little intimidating, but give me a chance to show you that it's not as bad as it really looks. It says if a function y equal f of u is a differentiable function, in other words, it has a derivative, and it's a function of u, and u is also a function of x, and that's a differentiable function, then y equals f of g of x, that's the composite part of this, is a differentiable function of x, and that derivative is given by dy over dx is equal to dy over du times du over dx. In other words, the derivative of y with respect to x is just the derivative of y with respect to u multiplied by the derivative of u with respect to x. You can also write it in terms of the composite, and if you write it that way, you say d dx, the derivative of that composite f of g of x with respect to x, is equal to f prime of g of x times g prime of x. Now give me a chance to make this make a little more sense. Let me talk about the different ways this can be written. There's really an advantage to writing it in each of these two different ways. The first way is nice for, among other reasons, is that it can actually serve as a memory aid. You can think of that dy over du times du over dx on the right as a regular product where the du's would cancel out or divide out, and you would get dy over dx again. So that sort of helps you to remember it. So in a sense, that's a good way of thinking about the chain rule because it makes it so easy to remember. But it's also useful sometimes to think of it as a composite function, that second way. So think of y as being f of g of x, where the inside part, the g of x, is a function in its own right, which we could call u. And if you think of it that way, it's sort of good to think of that as being, that composite as being made up of an inside and an outside function. In the composite f of g of x, we think of the f as being on the outside, so that's the outside function, and the g is on the inside. F is on the outside, g is on the inside. That's a very useful way to think about it. If you think about it that way, what the chain rule says, if you want to take the derivative of that composite, if you let y be a composite f of g of x, or if you're thinking of g of x as being u, it'd be y equals f of u. Here's the way you think about it. It's the derivative of the outer function evaluated at the inner function times the derivative of the inner function. Again, give me a chance. Let's say this again. It's the derivative of the outer function. So remember, the outer function is f. So the derivative of the outer function is f prime. But it's evaluated not at x, but at u, or at g of x. It's the inner function that's plugged into the derivative of the outer function. So it's the derivative of the outer function evaluated at the inner function, and then that is multiplied by the derivative of the inner function. Not so bad. It's the derivative of the outer function evaluated at the inner function multiplied by the derivative of the inner function. There are a lot of formulations of these ways you can think about these things. Another way of looking at it I find very useful is going back to this thinking of g of x as being u. If you think of it that way, then you have a function y equals f of u. In other words, y is a function of u, and then u in turn is a function of x. And if you think of it that way, then y prime, which is the derivative, is the derivative of f prime, evaluated at the inner function, which would be the u. So you get f prime of u multiplied by u prime. Now that breaks it down to its bare minimum, I think. if you look at it that way. The chain rule says if you got a function of the form y equals f of u, where u itself is a function of x, then the derivative y prime is a derivative of f evaluated at u multiplied by u prime. And what you have to remember in all of that is, no matter what you call u, eventually you're going to take the u's back out and write your answer in terms of x. And you'll see this through some examples. Speaking of which, let's find the derivative as a starting off point of this function y is equal to the quantity x squared plus 1 cubed. Now, according to the chain rule, we can take that derivative by applying whichever formulation of this makes more sense to me or to you, and use that formulation. I'm going to choose the one I presented just a second ago and look at it like this. If y is equal to f of u, then y prime is f prime of u times u prime. If you're going to think about it that way, your main goal is just to figure out what the u is. And the u is the thing raised to the third power here. So the u is the inside function. So it's the x squared plus 1. And notice that in your formulation of this, you're going to have to eventually calculate u prime. So you might as well go ahead and do it. The derivative of x squared plus 1 is just 2x. You're going to need that. The formula says you're going to have u prime. So what we've written now is y is a function of x. We let u be this x squared plus 1, so we end up with f of u equal u cubed. It's really the quantity 2x. It's really the quantity x squared plus 1 cubed, but we're letting u be x squared plus 1, so it'd be u cubed. And applying the derivative formula, the chain rule, all we have to do is take the derivative of the f function, the outside function, which is the u cubed, and then multiply it by the u prime, which we've already calculated. Well, u cubed is easy. If u is u cubed, if f of u is u cubed, then f prime of u is 3u squared. And then we have to multiply by the derivative u prime, which we've already calculated to be 2x. And what you have to remember is calling something u is a temporary procedure. Once you insert that u in there to help you do the calculation or the computation, when you're done with it, you take it back out again. So now that we're done with the derivative, we take the u back out and put in what it's equal to, which is x squared plus 1. And basically that's the derivative there. You can clean it up a little bit by multiplying the 2x times the 3 and getting 6x, but that's basically the derivative by the chain rule. When you first begin this, I really want you to try to apply the formulation of the chain rule that makes most sense to you and play around with it and try to do it sort of step by step and see what the rule is telling you to do. However, I don't want you to stay at that stage very long. I want you to very quickly move away from that so that you sort of internalize the procedure in terms of what the rule is saying, but then you learn how to do a lot of that sort of in your head by just thinking about it. I want to show that to you here. I'm not saying you should be there yet, but at some point, rather than doing it like I've just done it, I'd like for you to be able to do it like I'm about to do it. You don't necessarily have to get there right away, but sooner rather than later. So let's do this problem again without being so formal. And you're going to get better at this as you practice. And watching someone else do it is not practice. You have to practice yourself. And make mistakes. That's okay. You learn from your mistakes. You don't make them again. Or if you do make them again, you learn even better and don't make them the third time. So anyway, let's do this again. And I'm going to model the way I want you to be able to do it by the time you've really learned what this rule is telling you to do. So let's do it again. The function is y equals x squared plus 1 to the third. The chain rule says basically you take the derivative of the outside function and then multiply it by the derivative of the inside function. Well, the outside function here is the thing that gets cubed. So you think of that as something getting cubed. Formally, we put a u in, but I would say you don't necessarily have to do that, and you want to sort of get away from that pretty quickly. So I'm going to sort of think u in my head, but I'm not going to write it down. I know as soon as I put u in, I get u to the third, and the derivative is going to be 3u squared. And I know eventually the u is going to come out, and x squared plus 1 is going to go back in. So I want to get to the stage where I can think the substitution in my head, but never actually write it down on paper. So I'm going to write 3 times, that's an understood 1 right there. So it's 3 times 1 is 3. You write the base down, which is x squared plus 1, and then you reduce the 3 down to a 2. But remember, the chain rule says you have to multiply by the derivative of u, and in this case, the u is the inside function, which is x squared plus 1. And we wrote it down over here, u equal x squared plus 1. I'm sort of hoping you can think that in your head and not have to write it down, but as long as you need to, do it. It's better to write down more and get it right than to write down less and get it wrong. But I do want you to sort of migrate from writing down every little painful detail to just thinking some of those things in your head and less writing on paper. And I don't encourage less writing very often. But here I think to a point, it's going to help you in the long run. So what is this question mark for? That question mark is just to indicate that I haven't done u prime yet. Well, what is u prime? Well, u prime is the derivative of the inside function, which is the x squared plus 1 part. And the derivative of u prime then, the derivative of u prime, which would be u prime, is just 2x. And then again, you can take the 2x times the 3 and make it 6x. And notice you get the same answer. You wrote down a lot less. So at some point, I want you to migrate. I hope that you will migrate from writing more to writing less and keeping up with things in your head a little bit. But don't do it till you're ready. Practice, practice, practice. Earlier, we learned something called the general power rule that generalized the derivative rule for a function of the form x to a power. Using the chain rule, we can generalize it even more. I'm still going to call it the general power rule, but it's going to have even more power than it had before. Using the chain rule, I can make the power rule deal with composite cases where you have a function of x raised to a power. So if you've got a function of the form u of x raised to a power, then you can take the derivative using the general power rule, which is actually a special case of the chain rule. You're really not learning, you don't really have to learn it as a new rule, but it's just so much easier to do it that way. But when you think of the chain rule when it fits the form of a power rule that you've learned past, it's better to think it this way. And what you do is you take the power, bring it down front, take the function of x that's raised to power, just write it back down. Then you drop the exponent from n to n minus 1. In other words, you take it down one lower. And then you multiply by the derivative of u, which is the inside part. It's just the chain rule. But applying it to our old general power rule form just produces a formula that's easy to use without thinking so much of it being the chain rule. Another formulation of it would be to say something like this. d dx, the derivative of u to the n, is the same old power rule. You take the n and bring it as a coefficient. You drop the exponent n and make it n minus 1. But then you've got to go back and take the derivative of the inside, which is the u. So then you have to do u prime. It's the chain rule applied to this specific case, which is probably worth learning as a separate rule, even though it's really just a special case of the chain rule. Again, give me a chance to show you that it's not so bad. Suppose I wanted to find the derivative of the function y is equal to the cube root of the quantity x squared plus 4 squared. we've talked about this a little, but you have to be familiar with your algebra, especially in working with negative and fractional exponents. And remember, a radical represents a fractional exponent. And if you've got a cube root squared, you've got to be able to think of that as a 2/3 power. The index is always the denominator, and the power is always the numerator. And if it's a square root, the square root, usually you don't put the 2 in the index, but it's an understood 2, so a square root, if it had been a square root, would have been a 1/2 power. But in any case, you've got the quantity x squared plus 4 raised to the 2/3 power, and that's the form for which you have a derivative formula. In fact, it's the one sitting right here, the general power rule. So once you get it rewritten, you want to think of the x squared plus 4 as being the inside function. It's like the u. And the n is the power, and in this case it would be 2/3. So you're in your mind, even if you're not writing all this down, and you can, but even if you don't, you're thinking of the x squared plus 4 as being the u, and the 2/3 as being the n. And then apply the formula. The formula says you take the n, which is 2/3, and multiply it by the u, which is the x squared plus 4, except you raise it to the 1 less power. So you've got to take 2/3 and subtract 1. Well, 2/3 minus 1, which is 2/3 minus 3/3, is negative 1/3. So the power goes down by 1. But then you're not done. The chain rule, or in this case, the special case of the chain rule that we're calling the general power rule, tells you now you have to go to the inside function and multiply by its derivative. And clearly the derivative of x squared plus 4 is 2x. And now it's just a matter of cleaning it up a little bit. You'll probably want to multiply that 2x by that 2/3, and you'll end up with 4/3 x times the quantity x squared plus 4 raised to the negative 1/3. WebAssign is perfectly happy with that answer, so you can leave it that way. Practice, 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 and more practice. Watching me do it for understanding is fine, but watching me do it as a substitute for practicing it yourself is just a waste of time. You have to do it. Now let's take this problem a step further. This is the derivative that we just found. But what if I ask you now to actually find the equation of the tangent line at a point on that curve? So I just picked x equal 2, and the way I got that y that equal 4 is if you plug 2 back in here for x and do the calculation, you'll end up with a 4. They may or may not give you that 4. You may have to calculate it yourself. I just went ahead and gave it to you. But the point has to be on the curve, and that point 2, 4 is on that curve, the graph of that function. But what if I wanted to find the equation of the tangent line? As you know, the derivative gives you the slope of the tangent for any value of x. So from algebra, you know to write the equation of a line, you've got to know a point on the line and the slope of the line. And the slope of that line is going to be at this particular point. In other words, when x is 2, you need to plug 2 in here and here. So if you do that, you'll have to simplify. I noticed in that big set of parentheses, you've got 2 squared plus 4. 2 squared plus 4 is 8, and 2 times 4 is 8/3 in the beginning. So you get 8/3 times 8 to the negative 1/3. And again, you've got to be familiar with these negative exponents and how to deal with them. 8 to the negative 1/3 is the same as 1 over 8 to the positive 1/3. Now what's a 1/3? Once you get it to 1/3, you got to remember that a 1/3 is a cube root. So it's asking for you to take 8/3 and multiply by 1 over the cube root of 8. Well, the cube root of 8 is 2. Now you can divide that 2 into the 8 and get 4/3, or you can write it as 8/6 and reduce it to 4/3. But one or the other, you get a slope of 4/3. That's the calculus part, taking the derivative and getting the slope. That's the calculus part. The rest of it's algebra. I take the slope and the point they gave me, go back to algebra, mindset of just taking this thing as an algebra problem that you learned back in a previous algebra course. To find the equation of a line, you get a slope and a point, and you plug it into the point slope form. Y minus y sub 1 is equal to m times x minus x sub 1. The x sub 1 is 2, the y sub 1 is 4, and the slope is 4/3. Plug those values in. Simplify it. You're going to take that 4/3 times x and the 4/3 times negative 2. 4/3 times 2 is 8/3, so it's going to be minus 8/3. Then you're going to add 4 to both sides. And remember, 4 is 12/3. So you've got 12/3 minus 8/3, which is 4/3. So you end up with the equation y equals 4/3 x plus 4/3. That's the equation of the line that's tangent to the original function at the point 2, 4. You weren't asked to graph it, but let's slide that over and look at what the graph really is. That's what you've done. This equation, y equals 4/3 x plus 4/3, is the equation of that straight line right there that touches the curve, which is this original function, at the point 2, 4. So you need to, even when you're not trying to graph something, it's nice to think in your mind what you're doing, because sometimes that helps you understand it better. So, another example of the chain rule. Let's bump it up a little bit. How about this? Find the derivative of f of x equals to the quantity 3x minus 1 over the quantity x squared plus 3, that entire fraction squared. Well, it's a general power rule because you got something raised to a power, so we can apply the general power rule, which says that the derivative of u to a power is the power times u to the 1 less power multiplied by the derivative of whatever u is. So I'm going to do that. In this case, the u is the inside part. It's the thing that's raised to a power. So in this case, it's the fraction. 3x minus 1 over the quantity x squared plus 3. Well, what does the general power rule say? It says you take the exponent, which in this case is 2, and you write it down. Then you write the base down, the u. Don't change it, just write the u down. And reduce the power from 2. And they didn't write that here. It wasn't in there, but remember, that's an understood 1. So you don't need to write it in, but if it helps you to remember that you're reducing it by 1, you can. Raising something to the first power, you don't have to write the 1 down. But what you can't forget is that you're multiplying now, according to the chain rule, by the derivative of the fraction. Take the derivative of a fraction, that's the quotient rule that we learned earlier. Well, what does the quotient rule say? That's low d high minus high d low over low low. So we need to use the quotient rule on that. I'm not going to belabor every step because this is something you should have dealt with earlier, and you just need to practice and be particularly careful about the signs. But if you do low d high minus high d low over low low, you get what I've circled there in blue, and then there's a little bit of simplification going on. If you simplify what I've circled in red there, and being very careful with the signs, you'll end up with this. And then if you simplify it yet a third time, I'm sort of going from how it started out to a little bit of simplification, and finally in the third step, I've simplified it about as much as you can. And the only other thing that really happened was this x squared plus 3 times x squared plus 3 squared becomes x squared plus 3 cubed, because that's like to the first power. And when you multiply with like bases, you add the exponents, and 1 plus 2 is 3. Other than that, and WebAssign is perfectly happy to accept that as your answer. But it's up to you to practice this until you can do it. I cannot do this for you. You can watch me do it forevermore. And watching me for understanding is great. But it's not ever going to get past that with you unless you actually practice it yourself. So please do that. I will say that you could have worked this problem by squaring the numerator and denominator first and then taking the derivative if you had wanted to. In other words, square the numerator, square the denominator. And then you would have had a quotient rule directly. And the quotient rule again is low D high minus high D low over low low. And if you simplify that out, I won't go through this step by step, you end up with exactly the same answer you got before. So it's really and truly up to you to decide which way you're most comfortable with, which way you like to do best, which way you're less likely to make a mistake. I sort of think the first way was a little bit easier, but you have to make that decision for you. What I decide for me, it may not be the same thing as you decide is best for you. You make the decision and do it that way and then practice it that way. Let's end with an application. This problem says the number of bacteria in a culture after T days is modeled by this equation. Capital N is equal to 600 times this quantity. I'm not going to read the whole thing, but it's a function of T, where T is the time, but it's in days. So N is the number of bacteria, but the time is in days. And we're finding the rate of change. Anytime you see rate of change, anytime you see slope of the tangent line, those are key words or phrases that immediately tell you you have to take a derivative. But before you can take that top derivative, you probably want to write this fraction as a negative exponent. So if you bring that t squared plus 2 quantity squared up to the numerator, it becomes a minus 2. Remember, if you move something from numerator to denominator, vice versa, it changes the sign of the exponent. Because that fits the rules you know how to deal with. You could actually leave it as a quotient and use the quotient rule, but as we've discussed earlier, when one of the terms, numerator, denominator, or when you're doing product rule, one of the factors, when it's just a number, it's much easier to rewrite than to do it using that rule, although you're perfectly welcome to if that's easier for you. But I would rewrite this. And once you rewrite it, you might even want to go ahead and multiply through by that 600 just to get that out of the way. You could just leave the 600 there and take the derivative of the function and multiply after you take the derivative, but I sort of prefer just multiplying it out. But once I get this written out, I know because it said rate of change, I have to take a derivative. Well, the derivative of 600 is 0. That's just a constant. So now, to get the rest of it, I got to use the general power rule, and it says take the exponent and multiply it by the coefficient. Well, that's a negative 1800 and a negative 2. When you multiply those together, you get 3600. Then you write the base down, which is t squared plus 2, but you decrease the power by 1. So that minus 2 goes down by 1 and becomes a minus 3. And you're not done yet. The general power rule says then you have to take the derivative of the inside, the u function, what we call u sometimes. That's the t squared plus 1, and the derivative of t squared plus 1 is 2t. And you found the derivative. Now, WebAssign is perfectly willing to accept that as an answer if you go ahead and multiply it by 2, I suppose. But I went ahead and dropped that negative 3 into the numerator and made it a positive 3 only because they're going to ask me to plug in various numbers. And I think I can handle it better if I go ahead and take that t squared plus 2 to the negative 3 and write it as 1 over t squared plus 2 cubed. Basically, the only reason I did that is because I knew I was going to have to plug in numbers, and it's just easier for me to plug in numbers without those negative exponents there. At this point, it's an arithmetic problem. They want you to plug in t equals 0, t equals 1, t equals 2. So if you plug in t equals 0, you're just taking a 0 and plugging in everywhere you see a t into the derivative. And if you calculate that out, you'll find out it's 0. So the rate of change in bacteria per day on day 0, in other words, right at the very beginning, is 0. After 1 day, t equals 1, you go in and plug 1. You're plugging 1 in for t into the rate of change formula, which is the derivative. And again, I won't bore you with the details, but you get 266.67. It keeps continuing, but they said to round it to the nearest 10th. Actually, I round it to the nearest 100th. But if you do the nearest 10th, that would actually be 0.7. So let me change that. 0.7. I thought it said the nearest 100th. Easily fixed. And then do it again, and you get about 66.67. Again, if you're rounding it to the nearest tenth, that becomes 0.7. So that'd be 66.7. It's just arithmetic at this point. And there are actually two more. They also want us to do it for t equals 3. If you plug 3 in, simplify it, you get about 16.23. And again, they did say tenth, and I was doing it as a 100th. So I do want to follow the rules. So that'd just be 16.2. And again, going back here, that'd be 0.7, and that would be 0.7 to the nearest tenth. And then they want to do it for t equals 4, so you plug 4 in, and you get about 4.94. And that would be 4.9 if you do it to the nearest tenth. So I originally did it as if it was said to the nearest hundredth, and as soon as I reread the problem and realized they only wanted tenth, I made that correction. And the last question, F. What can you conclude? Almost all of them mention rate of change. Rate of change, rate of change, rate of change. This problem just says the number of bacteria is only increasing during the first day. Remember, the derivative tells you about a rate of change. This is the only one that doesn't mention the rate of change, so you can just eliminate that right away. It doesn't mention rate of change. It's not going to be that one. It's going to be one of the answers that mentions rate of change, because that's what this tells you about, the rate of change. So now I've eliminated one answer. It's only one of the four. So let's just read through them. The first one that's still in contention says the rate of change of the population is always decreasing. Well, it's obviously not. It went from 0 to 266 point something. But then it says it's only decreasing over here. That's not true. It went up. So it can't be that one. It can't be A. So we've knocked out the first two possibilities. So read the next possibility. The next possibility says after the first day, the rate of change is increasing. Well, after the first day would be going down this way. It's actually going down. It goes from 266 to 66 and then down to 16.4. So it's not going up. So it can't be the increasing. That's not right. The next one says, well, actually, I noticed that it says increasing down bottom here too, so I can eliminate that one. The only one that says after the first day the rate of change in population is decreasing is this one. So it's obviously that one. Because after the first day, it goes, I'm just going to drop the fractions. It goes 266, 66, 16, and, almost 5. It's going down. It's decreasing after the first day. You can have various applications, not always going to be bacteria rate of change, but the idea is the same. No matter what they say in the problem, if they call it a rate of change, you're given an equation, you're going to take the derivative, and if they ask you for the rate of change in any particular values, you simply plug those values into the derivative. So again, you've got to understand the concepts, and I think the videos help you with the concepts, conceptual understanding. Some advice I think the videos are very helpful with. Just some validation that you're understanding the process, refreshing your memory on some things. All that is a useful use of the videos, but it does not take the place of practice, 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 practice. Please believe me. So go practice this stuff. I'll leave you with a list of all the derivative rules that we've covered, up into including the chain rule that we did in this lecture. You need to be familiar with those, able to use them when needed, and again, practice, practice, practice.